Welcome back to this first course in general physics. And now we are still talking about the topic dynamics of a particle, and we are in the third part of this topic. In this lecture, we will finish talking about the connection between force and Newton's laws of motion. Under this umbrella, we will talk about dynamics of a circular motion, which we will discuss for the first time. And then we will move to another topic which concerns one of the properties of material objects, which is energy. We will talk about work, the process by which energy is transferred to and from an object. So we will define the concept of the kinetic energy. We will discuss the work definition and how to calculate it. And in this lecture, we will only discuss the work done by a constant force, both in magnitude and direction. And then we will have a simple application to work done by gravitational force, being a constant force. So this is the last topic that is going to be in this lecture. And as we mentioned, now we talk about the dynamics of a particle or an object moving like a particle around a circular path. Often we encounter the motion of objects around a circle, or an object would be going around a curve. The curve is sort of an arc or part of a circle. So moving around a path that it looks like a circular path or part of a circle is the field of this topic that we are discussing, which is the motion on a circular path, or the dynamics of circular motion. We will be discussing what type of forces would act on such an object which is moving around such a path. Before we have to categorize the motion around a circular path into two types. One type is called the uniform circular motion. In this type of motion, the object moves around the circular path with a constant speed. So the magnitude of the velocity of the object moving around the circle is constant, the magnitude, although the direction is changing with time in order to go around the circle, but the magnitude is different, is the same. The magnitude is constant at any point on the path, at any point in time. That is called the uniform circular motion. This object moving uniformly, although this name could be misleading, uniformly meaning with a constant speed, with a constant magnitude of the velocity around the circular path, is accelerated. It could sound strange to say that such an object which is moving with a constant speed is accelerated. Actually, it's not that strange, because we have to remember that the velocity is a vector. A vector can change in one or two of the following ways. A vector quantity would change if its magnitude changes. That's one way of changing a vector quantity. The vector quantity can change if its direction changes with its magnitude being the same, just like a vector turning in space. Then with the same magnitude but different direction, we say that this vector quantity is changing. Or in general, a vector quantity can change both magnitude and direction. So in the uniform circular motion, in this case, the magnitude of the velocity is fixed, is constant, but the direction of the velocity is changing, which means that the velocity is changing. There is a delta v as time goes. Having delta v vector as time goes implies that we have acceleration. Since we know from the definition of acceleration, the acceleration is defined as delta v over delta t. So only changing the direction of the velocity would imply that the particle is accelerated. Now, this particle is accelerated towards the center. That means the direction of the acceleration is always sideways. It is perpendicular to the direction of the velocity of the object and is directed towards the center. So wherever the object goes, the acceleration is always sideways and directed towards the center. Why is that? This is particularly logical, because if the acceleration were not perpendicular to the direction of the velocity, if the acceleration has a component in the direction of the velocity, then the velocity will change. The particle will accelerate in the direction of the velocity, and the velocity will increase in magnitude. But being constant in magnitude, that means the acceleration does not do anything to change the magnitude, which means it is perpendicular to the velocity. Perpendicular to the velocity always, in order to maintain the magnitude fixed, that means the acceleration should be directed towards one particular point as the particle moves around the circle, which is exactly the center of the circle. So the radial acceleration, or what we call the centripetal acceleration, is radially inward. It is directed towards the center of the circular path. That is the direction of the acceleration of the particle moving around the circle. What about the magnitude? The magnitude of the acceleration can be calculated in different ways. We will not involve ourselves in calculating this acceleration. It is to be known for the time being that this centripetal acceleration, which we call a sub r, to imply that it is radially directed. It is directed radially inward along the radius of the circle. A sub r is equal to v square divided by r, where v is the velocity of the particle, and as we said, it has a constant magnitude, and r is the radius of the circular arc, or the circular path on which the particle moves. This formula, I will not, as I mentioned, I will not derive it, but it can be derived by the definition of the acceleration, taking a equals delta v by delta t, taking 2 points, determining what is delta v from one point to another, determining what is the time interval, which is the arc divided by the speed of the particle, and dividing these two by each other, taking the limit where delta t goes to 0. That means the arc goes to 0, the arc length goes to 0, in which case sine theta, which is the angle that the particle makes with a given with an axis, goes to 0, in which case sine theta would equals to theta. Taking all of these into consideration, that will lead to the development of this formula, which gives the magnitude of the centripetal acceleration. I motivate you to try to find it. This is not the only case that we encounter in circular motion, however. Sometimes we have objects orbiting a given trajectory, going around a circular orbit or a circular path, where the magnitude of the velocity or the speed of the particle changes from time to time. As we saw from the previous discussion, the radial or the centripetal acceleration does not lead or entail the change in the magnitude of the speed. If the magnitude of the speed is changing, that implies that we should have a component of the acceleration in the direction of the velocity. That is the only component that would lead to changing the magnitude of the velocity. And this way, in this type of motion, we will be having two components for the acceleration. One component is the component that is in the direction of the velocity, which we call the tangential component, because it is always tangential to the path, to the circular path. It's in the direction of the velocity. So, and that is the tangential component, which is responsible for changing the magnitude of the speed of the particle from time to time. And the second component is the centripetal component, which is the radial component, and that component is the component that is responsible for curving the path of the particle to make it go around a circle. So the centripetal acceleration is responsible for curving the path of the particle, while the tangential acceleration is the acceleration that's responsible for changing the magnitude of the velocity. If the magnitude of the velocity is changing due to a tangential acceleration, then the tangential acceleration is defined as a sub t is equal to dv by dt, the range of the change in velocity divided by the change in time. The rate of change of velocity with time is the tangential acceleration at a specific time. And this figure shows a particle moving around a circular path with its acceleration written in component form, where we have a sub r is the radial or the centripetal acceleration given by the magnitude v squared over r, and a sub t is the tangential component of the acceleration, which is tangential to the path and given by dv by dt. The acceleration means that there must be a force acting on the object according to Newton's second law. If a particle is accelerating, that means there must be an external force acting on that particle. So that means any particle that is moving around a circular path, there must be a centripetal force acting on the particle in order to ensure that the particle moves around a circular path. What is the centripetal acceleration? What is the centripetal force that is responsible for the centripetal acceleration? Is the centripetal force a new type of force, of physical force? The answer is no. It is not a new type of force. The centripetal force could be any of the known forces to us, any of the forces that we have discussed before, or some other forces that we have not discussed. For example, if we have a light bulb hanging from the ceiling and we push the light bulb sideways, it starts going on a circular motion, on a circular arc. And what is the centripetal force that is responsible for this circular motion? The centripetal force in this case is the radial force acting on the bulb. And this is the sum of two forces: the tension in the cord and the component of the gravitational force acting on the bulb along the direction of the cord. Another example, if we have an object attached to an end of a cord or a rod, and it is circulating with the other end of the rod or the cord fixed, then again the tension in this cord or in this rod is the centripetal force that is responsible for this type of motion, circular motion of the object around the circular path. In these two examples, the centripetal force is a contact force, which means that the force, the source of force, is touching the object. It's a contact force, like push or like a pull. You have to touch the object in this type of forces. However, sometimes the centripetal forces are not contact forces, forces that act on an object from a long range. For example, the gravitational forces that could be centripetal forces. Earth is going around the sun in almost a circular orbit. If we consider it a circular orbit, then the attraction, the force of attraction that the sun attracts the Earth is the centripetal force that ensures this circular path of the Earth around the sun. However, this force does not touch Earth. It acts on it from far away. This is a non-contact force. It is a long-range force. So as we noticed, centripetal forces do not have to be contact forces all the time. The magnitude of the force, of the centripetal force, is given by, as we can see from Newton's second law, F sub r is equal to m, the mass of the object which is moving, times its acceleration, its radial or centripetal acceleration, a sub r. So applying this law, second law of Newton, we would arrive at the formula which gives the centripetal force, which is responsible for the centripetal acceleration, Fr, given by Fr is equal to mv squared over r. We have to remind each other that this is not a law of force. F sub r is equal to mv square over r is only the magnitude of the force. But what is the force? The force is any physical force, like gravitational force, for example, like the tension, for example, or any. So mv square over r is only the magnitude of this force. At this point, we are ready to go for the discussion of another topic, which is work and energy. We start by a definition. Energy is an intrinsic property of an object or a collection of objects that is connected with a state or a condition of that object or that collection of objects. Kinetic energy is one type of energy, and this type of energy is associated with the motion of the object. If the object is moving, we say that it has kinetic energy. If it is at rest, we say that its kinetic energy is zero, or it does not have kinetic energy. So kinetic energy, we symbolize it by K, is associated with the motion, with the state of motion of the object. The kinetic energy is defined as 1/2 times the mass of the object that is moving times the square of its velocity. So we notice that the faster the object is, the more energetic it is. And the proportionality constant between the kinetic energy and the velocity square is the mass of the object. Because having two objects moving with the same velocity, if one of them is heavier than the other, more massive than the other, then our experience tells us that that heavier object which is moving with the same velocity is more energetic than a smaller object. So if we have, for example, a mouse moving with a certain velocity and an elephant moving with the same velocity, the elephant is more energetic than, it has more energy than the mouse. The international system of units for the energy is the kilogram meter square per second square, because it's simply mass times velocity square. And that unit is called the joule, named after John Prescott Joule, the English scientist of the 18th century. Now we come to the definition of another factor in the discussion of energy, which is work. The concept of work is connected intimately to the concept of energy transfer to an object that is moving or from an object that is moving. So if we have an object that is moving with a specific velocity, with a given speed, for example, we can always change this speed of the object, thus changing its kinetic energy. If we change its speed, that means we change its kinetic energy. But according to Newton's second law, we cannot change the velocity of an object, the state of motion, unless we apply an external force on it. So this change in the kinetic energy of an object is associated with always with an external force acting on the object. When the force acts on the object and changes its kinetic energy, we say that the force did work. So the work is the transfer of energy. Is energy transferred from the object if we reduce its velocity by doing work, or energy transferred to the object if we increase its velocity by doing work on it via a force, by a force. So work is energy transferred. By doing work, we notice that the energy increases or decreases. And doing work is the process by which this transfer occurs. So work is energy transferred to the body, and doing work is the process by which we do that. Doing work would lead to a change in the velocity, and thus a change in the kinetic energy, as we mentioned. From our experience, the work which is related to the transfer of energy is dependent on the angle between the applied force and the direction of motion or the displacement of the object. And this is obvious because we notice that if an object is moving in a given direction, and if we only apply a force on it that is sideways, meaning perpendicular to its direction of motion, then the magnitude of the velocity does not change, as we noticed in the case of the circular motion, does not change, which means the kinetic energy does not change. So that means there is no transfer of energy to the object or from the object. Its kinetic energy didn't change. That means there is no work. Although we have applied a force, but still there is no work. That means the work does not depend only on the force applied and the magnitude of the force applied. It also depends on the direction of applying that force. There should be a component of that force that is directed in the direction of motion of the object or in the direction of the displacement of the object in order to ensure having done work and having transferred energy to, in the case of increasing kinetic energy, or from, in the case of decreasing kinetic energy of the object. Thus, we take in the beginning a specific example, a simple example. If a constant force is acting on the object, if the constant force is acting on the object, the work is defined as F dot D, where F is the force vector that is applied to the object, and D is its displacement. F dot D is simply F magnitude times D, the displacement magnitude, times cosine phi, the angle between F and D. And this way, we have taken into consideration only the component of force that is in the direction of the displacement by taking F cosine phi. So F cosine phi is the component of force in the direction of the displacement times the displacement, since only this component is the component that is responsible for changing the velocity or for accelerating the object and thus changing its kinetic energy and thus leading to the transfer of energy. So this is the definition of the work done by a constant force. And if we assume for the time being that this applied force is a single force, only this force is applied to the object, or if we assume that F is the net external forces acting on the object, in case if we have many forces, we take the resultant of these forces and we consider that this F is the resultant or the net external force acting on the object. In this case, we arrive at an important principle, which is the kinetic energy work theorem, derived from our previous discussion, based on the fact that work is energy transferred to the object, which implies that the work done by the force, by this net external force acting on the object, is simply the difference in its kinetic energy. Since, as we said, work is energy transferred to the object, so the work is equal to the difference in kinetic energy of the object. Now, if the force applied is not a single force, but rather a collection of forces, then the work done by the collection of forces, F1, F2, F3, is simply the sum of the works done by all the forces. So the total work done by all the forces is W1 plus W2 plus W3. That is the total work done by all external forces on the object. And since all the work done by external forces acting on the object is the work that is responsible for the energy transfer, then we arrive at the conclusion that the difference in kinetic energy, delta K, for the object is simply equal to the sum of the work done by all the external forces on it. Now, as we defined the work done by a constant force acting on an object, we will be discussing a specific example, which is the work done by gravitational force. We know that an object near the surface of Earth is affected by the gravitational pull on it, which is its weight, m times g. This is the force by which Earth pulls on the object. This force is, as usual, a vector, which has a magnitude of mg and directed downward towards the center of Earth. From the definition of the work done by a constant force, we have the work done by gravity on an object which is experiencing a displacement d, a displacement vector d, is given by mg dot d, which is the usual definition for work done by a constant force. And if we assume that the angle between the force and between the displacement is phi, if we call it phi, then the work done by gravity is simply the magnitude of the mass of the object times the magnitude of the gravitational potential, the gravitational acceleration, times the magnitude of its displacement, times the cosine of the angle between the gravitational force, which is downward, and the displacement of the object, to be decided later what it is, whether the object is going up, whether the object is going down, whether the object is going sideways, and so on. So as an example, if the object is going sideways under the influence of gravity, then the displacement is sideways and the force is downward. The angle between them is 90 degrees, and thus cosine 90 is 0, of course, and thus the work done by gravity is 0. Thus, if we move if an object moves horizontally in the field of gravity, the work done by gravity on that object is 0. Now, if we have a rising object, if the object is going up under the influence of gravity as a special case, what is the work done by gravity on this object? We go back to our original definition, which is work is equal to m times g times d times cosine the angle phi between the force and the displacement. And we ask ourselves, in this case of the object rising, going up, what is the angle phi between the force and the displacement? The force is pointing downward, which is the gravitational force, and since the object is going up, that means the displacement is upward. That means the angle between the force and the displacement is 180 degrees. And cosine 180 degrees is -1. And thus, the work done by gravity as the object is going up is simply minus m times g times d, where d is the upward displacement of the object. This work tells us that as the object is moving upward, the gravitational force does work on the object which is negative. That means it transfers kinetic energy from the particle to somewhere else. To somewhere else, we will discuss it later. Where does it go? But for the time being, taking into consideration the work energy theorem, the kinetic energy work theorem, we notice that the work is negative, which implies that the gravitational force does work to transfer energy from the object. So it reduces its kinetic energy. And that is evident since if we toss a particle or an object upward, it starts with a given speed, and then this speed in magnitude is reduced until it stops somewhere on the top. That is why that is the meaning of the negative work done by gravitational force on an object as it rises. Thus, in this case, as we said, the object loses kinetic energy as it goes up until it stops, and then after that it flips its direction and starts going down. Now we have a second case of motion of an object under the influence of gravity, which is the falling object. In the case of a falling object, the gravitational force, as usual, always points downward, and the displacement in the case of falling is also downward. So the angle phi between the gravitational force and the displacement is 0 in this case, and we know that cosine 0 is equal to +1, which means that the work of gravity in this case of falling object is equal to plus m times g times d, where d is the vertical displacement downward, or the distance the object travels downward. The plus sign of the work done by gravity simply implies that the object is gaining kinetic energy because the work is positive. That means energy is transferred to the object. And also, this is evident by observing a falling object. If we hold an object in our hand and then we let go, it starts with zero velocity and it starts speeding up and gaining kinetic energy as it goes down. This is because the direction of the displacement is the same as the direction of the force, and thus the work done by gravity is positive, and there is accordingly an increase or a gain in the kinetic energy of the object. The object gains kinetic energy. As a final example, we can ask ourselves, what if we lift an object from one point to another point upward? What happened? Although the object is rising, still its kinetic energy is not changing. It starts from zero velocity, it ends with zero velocity. What happened? Where is the work done by gravity? Where did it go? Actually, in this case, it is not only gravitational force that is applied to the object. The object is acted upon by actually two forces. One of them is the gravitational force, and the second one is our applied force. We apply a force in order to lift the object upward. And if we calculate our work done by us as we lift the object up, it turns out that the work that we do in lifting the object is a positive quantity, which is equal to mgd positive, because our force, our applied force, is in the direction of the displacement, while the gravitational force does work that is equal to minus mgd, because the direction of the displacement is opposite to the direction of the force, in which case the total work done by the two forces, or all the net external forces on the object, is zero, and thus the kinetic energy of the object does not change, as we notice. The same thing applies to lowering the object from one point to a lower point. Also, the work done by us is negative, while the work done by gravity is positive. They are equal in magnitude, and the net work is zero, and the particle does not, or the object does not change kinetic energy. At this point, I would like to end this lecture and thank you for your attention.